People joining. Okay, I think we can start. Good afternoon, everyone, for the second MULTHEM training session, which is overview of joining technologies for similar and dissimilar materials within the MULTHEM project. Like I said, this is our second training session. First training session was conducted last Monday on 24th of March. This training session will be conducted by Martha and IBK. So the first half of the training session will be conducted by Martha, and the second half of the training session will be conducted by IBK. I would like to go over some general housekeeping rules. Please make sure to keep your microphones on mute during the presentations, and we would encourage all of you to reserve your questions until the end of the training sessions. And once the full training session has finished, you can unmute your mic and direct the questions to the trainers, or alternatively, you can use the chat box to drop in your questions. So yeah, I won't take too much time. I will pass it on to Martha to start the training session. Thank you very much.
Thank you very much, Janith. Welcome everyone from Europe to this training session, the second one, based on welding, well, let's say innovative and cross-cutting welding methods. I'm gonna share my screen. One second. Okay. Can you see my screen, full screen?
Yes, Martha, we can see.
And you can hear me correctly, right?
Yes.
Okay. So, I'm going to start with the introduction of the robotic friction stir welding technology, based mostly in metal, and then metal composite we will follow by my partner Ivike from Fraunhofer. But this is all included in the MULTHEM project, which is the multi-material additive manufacturing for lightweight and thermal management European Horizon Europe project, as you may know already. So let's start with the introduction to friction stir welding. I don't know if the attendees knows about this technology, but basically it's a solid state welding process used to join pieces without melting them. This is really interesting because most of the technologies for welding are based on the melting of the components or melting of the different metals to keep it welded. So this one is really different in this sense. So the process is basically carried out by using a rotating tool, which is composed by a pin and a solder that moves along the joint line of the components to be welded. So the tool basically softens the materials by plastifying them, and it allows the tool to steer the material. In this case, for example, you can see in this video we are joining aluminum plates. So how it works, basically, the first step is the rotating tool with a solder and a pin is inserted between the two materials to be joined. The second step, let's say, is the tool plunge into the material, creating heat because of the friction between the tool solder and the material surface. So basically, the responsible of the heat input is the friction between the solder and the surface of the material. And then the pin, which is already inserted in the plate, in this case, taking advantage of the plastifying of the metal, creates a flow by steering the material and creating a super high strain distortion field. So it means like we are forcing a very, very high distortion in the material and a process related with recrystallization and with the advantages that we will see in a second. The fourth step is that the tool moves along the joint, so making a line at the same time that is rotating and mixing the material. So the joint line blurring the limits between the components and keep it welded at the end. So a bit of introduction to the friction stir welding is very important to define this technique as a severe plastic deformation technique. So what does it mean, right? Into the left, you can see in the screen example plastic deformation techniques. We can find different ones, for example, ECAP, which is equal angular channel, or HPT, high torsion. So in this case, for the friction stir welding, it is a method for metallic material in which large deformation are induced under high hydrostatic pressures. So it provides the possibility to strengthen the alloys to levels that may exceed those obtained by other traditional methods, right? So, which is not really severe. So it improves the microstructure by increasing the misorientation of the grains, also by reducing the grain size and increasing the crystallographic texture. So it means at the end a very good mechanical qualities and a very good quality in general in the welding. So important detail within the severe plastic deformation techniques, they all follows the same rule. The overall dimension of the severely deformed material do not change after the process. So this is important. We should not change the dimension at the end of the welding in this case. So, as we mentioned, as a solid state, we have different advantages related with the process itself, the nature of the process, which is the main one for sure. It's a solid state process, so the material don't melt. Not any gases are within the material, so the porosity is really, really low and really reduced. So we can join material that are difficult to weld traditionally, and also we can weld dissimilar materials, right? So it's really a typical example of friction stir welding, the welding of aluminum with copper, or even aluminum with steel, which is something, for example, performed by the army, the American army, the welding of this steel and aluminum. Okay, so we can create durable welds with low distortion and pressure proof, and watertight welds also if it's needed. So we can reduce the rectification cost and distortions after, for example, additive manufacturing process. We can create high strength at high temperature welds in general, high densification, and we don't have any splatter or gas emission during the welding. It is really safe to the operator, and we don't need to any material addition to the welding. Okay, so we are only using this tool, and that's it. So in this case, for example, in ZTMet, we have this model of the KUKA robot, KR 500. So, and also we are using a Thistir spindle, which is a brand from Germany. So this severe plastic deformation is using a spindle and a tool, as we mentioned. The process parameters development for an industrial or for an experimental dissimilar multi-material is really the key point of this process. in this sense is similar to additive manufacturing. So everything is around the parameters of the process. And the materials possible to weld is steel, light alloys, especially aluminum and magnesium alloys, also copper. We can weld titanium. It depends also on the thickness of the components to be welded. So many sectors can use this technology, industrial in general, automotive, batteries, aerospace, naval, and others. So specifically, industrial advantages of robotic friction stir welding is it's really energy efficient and environmentally friendly. It's a process that is easily, once that you have the parameters and the conditions for your material, you can automate. It's really automatable process and repetitive. We can have a super high quality welding in aluminum, for example, in different kind of aluminums, which are different to weld by other technologies, with high strength and good microstructure, and also with excellent corrosion behavior and wear resistance. So we consider that this process is very good for post-processing in additive manufacturing processes in general. So here you can see the prototype that we have in ZMet. So different components are here in the picture. You can see the tool, which is going to be explained in a second, the clamping system and the holder, and also the spindle and the robot for sure. So it is really important, the clamping system for this process, because the components has to be absolutely fixed, and if not, you can have some defects on your welding. So it's a critical point. So what about the configuration, right, of the layout of your components? In this case, we are just watching a plates, but you can weld also circular geometries, and also you can weld the plates by different configurations. So you can make it in an edge butt joint, or in a square or lap joint, or multiple lap joints. So it is really versatile technology. So important to take it into account. The final characteristics of the joint depend largely of the chosen configuration, right? And also the thickness of the materials is really critical, because it's going to be important at the moment of choosing the tool, and also choosing the layout. Okay, how to weld these materials. So related with the tool, it theoretically is a non-consumable tool, but in the practice, it is true that at the end, after several weldings, the tool has to be changed. But in ZMet, we have developed, for example, a method for additive manufacturing to manufacture the tool in Inconel 718. And the behavior and the performance of this tool is really good. So you can combine, it's a successful use case for additive manufacturing and friction stir welding. So you can manufacture your own tools depending on the configuration of the welding. Okay, so in this case, as you can see, we manufacture the tool, and then we have to machine it a little bit before we are using it. Okay, so we are saving cost and saving time. So here more details about the tool that we are using. As you can see, the pin geometry is really simple. So we are not using complex geometry, and it is sufficient and good for the weldings in our case. So it's not always necessary to use a really complex geometry for your tool, okay? So it's always easier to start with the simple geometry, and then you can increase the complexity of the tool depending on the quality of the welding after. So if we continue the workflow, how you have to prepare your material for the friction stir welding? Well, So you have to take the plates. In this case, you can see aluminum commercial plates. So it's really important to measure the thickness, and it is important also that the surface on one side and the other of the welding is the same. So the tool, once that is advancing, finds a very flat surface. Okay, so in case you want to, for example, weld something circular, it's okay. You can weld on circular surfaces, but the both sizes have uh, needs to have this very flat surface for the tool. Okay, it's a key point also during the process. So also the fastening system is important. As I mentioned it before, the clamping system is really important because the plates and the components needs to be absolutely fixed. Okay, so once that the tool is advancing, the material is absolutely on the same place, right? So not any defects it's induced. So, and another important point is the separation between the two plates. You need to consider that the separation between the two components before the welding is absolutely zero. So the components needs to be in contact, absolutely in contact. Okay? Important parameter before the welding. Okay? So let's go for the main process parameters for friction stir welding. So for sure, the rotational speed, really critical. It is related directly with the heat input of the process and for sure with the temperature that you are going to achieve during the process. Also the linear speed, what's the velocity of the tool during the welding, the tool geometry, as we mentioned, also the tool penetration. These hydrostatic forces are really important for the compactation of the material. Okay, so the tool penetration is really critical. The dwell time, which is related with the time that the tool is already inserted between the two components and frictioning without advancing. Okay, this is the dwell time, the time that you are in the same point, just rotating before starting the welding. And also if you are using any tiled angle, which means if your tool is directly going 90 degrees to your surface, or you are putting a tilt angle, which is a variety, right, in the angle between the forces, so you can more or less improve or facilitate the process. Okay, so it is something that depends absolutely on the material and the thickness that you are welding. So selecting the correct parameters for the process is really in this technique a key point to achieve a valid joint. Okay, so to perform a weld using the friction stir welding equipment, first, we have a program detailing the process steps. It is something important to have a technician which knows very well how is the language of the robot and the spindle, so you can match and you can introduce as an input the parameters. So remember, they are mostly the rotation and the advancing speed. And so you can also work with the dimension control. Okay, so in this case, you have two possibilities to work with the friction stir welding. You can work controlling the forces, so you can put as an input in your program a specific force during the welding, or in our case, for example, we are working with the different dimension control. So we said to the robot, okay, you have to go to this dimension within the pieces, and then you have to maintain this and during the welding. So two possibilities for that. So before we are starting the process, we have a preload phases, then the drilling, which is the process of inserting the tool into the material, and then we can start the welding. Here a video of the process. As you can see here, the tool is rotating, and then the solder is heating up the material and plastifying it, and then advancing. So, okay, so what's critical about the visual inspection of the material? So here, for example, in the left side, you can see visually that the shoulder didn't touch so much the surface, so you have this defect, which here the welding is not valid. So in the right of the slide, you can see a correct aspect of friction stir welding, which is the dimension of the welding should be the same as the diameter of the shoulder. It means that the shoulder really push and really touch and friction the surface of the material. So how to check if the welding is correct or not? In this case, generally, if your parameters are correct and you perform correctly the welding, you have high densification, you don't have porosity, a very fine microstructure, and exit microstructure with a grain size. I put 0 until 5 microns, but in most of the cases, if you are working with a very low heat input in general, which is the relation between the rotation and the advance, you can have grains under the micron. So sometimes you have nanometer grain size, which is really good for the mechanical properties. So here in this scheme, you can see the typical transverse inspection of the welding, in which the thermal part, the thermal affected part of the welding is into the left and into the right, and in the center you can see a very fine microstructure, not differentiating, right, the grains, because they are really small, and the different zones, right, the stirred zone and also the thermomechanical, the TMAF zone, and also the thermal affected zone. Okay, so if you want to check, for example, in an electron microscopy, your microstructure, then I hear the best place to take a sample is exactly when in the place that the yellow rectangle is located within the S-sit zone. Okay, another examples that we have checked in Thetameter. In this case here, you can see aluminum silicon magnesium original material manufactured by laser powder bed fusion, and then we performed the friction stir weld. So you can see, for example, that the advance and the retreat zones are sometimes slightly different. It means that the advanced size is the part in which is the vector of the rotation is coincident with the advance of the tool, and is different in the retreat, in which the rotation vector is the opposite of the advance. Okay, so it's another detail to take into account that sometimes is important, because it's not exactly symmetrical to the center. But the microstructure inside, again, really fine, really equiaxial, and out of the welding, you can see the typical structure from additive manufacturing with the welding tracks. Here a detail, of the welded area, how the microstructure in this central picture, how it changed from the left with these welding tracks. And once that you are checking the welding, the friction stir welding side, then the microstructure is absolutely fine. So you cannot differentiate any structure or any line with the limit between the two components. Okay, so absolutely erased. So here another important part of the friction is the mechanical characterization of the weldings, and sometimes the plates are really, really thin. So we need to machine this kind of bone tensile samples, really thin samples, but is the only way to check how is the strength of the welding. And in this case, you can see that we machine some samples in line of the welding and other transversal samples to check in both directions how is the tensile behavior of the welding. Okay, to check. This is an example of some results at different temperatures. Very good quality, mechanically speaking, for an aluminum. In this case, is the aluminum 2024, welded by friction. And then, for example, we can achieve 400 or 450 megapascals in aluminum at room temperature, which is really good. And this is because of the fine microstructure and very homogeneous microstructure within the welding. Another mechanical characterization, which is really interesting and very visual, is the harness testing. In this case, I share the Vickers instrumented microindenter. So we can measure in the same aluminum. This is an example of aluminum 2024. And also we can see how the center of the welding in both cases, in different samples, is higher than the matrix, the rest of the material. So we are increasing also the hardness in the welding part. So basically, this is a summary of the process for performing a friction stir welding in light alloys and how to check very basically if the welding is correct or not. So I don't know if anyone has any question. I'm open to answer anyone. Thank you. Okay, if you have any question later on, so we can discuss at the end. So I will give the floor to my colleague Ibike, and then at the end, if anyone have any questions, so we can discuss. Thank you.
Thank you for the introduction, Marta. Can everybody see my screen?
Yes.
Okay, yeah, many thanks. Firstly, sorry for my voice. I have a cold at the weekend, that's why sorry, apologize for my voice. And my name is Ibike Alçınyız. I am working as a research associate and RD project manager at Fraunhofer IPK in Berlin. I would like to explain the joining of dissimilar materials within the MULTHEM project. Sorry. Yes. I would like to first explain what is the multimaterial, what's the aim of our project as a MULTHEM. We would like to develop new innovative multimaterial system to produce the better, good mechanical performance, good thermal performance, lightweight. Yes, and for this you are using also additive manufacture technologies, especially for the produced complex part. But for example, our cases for our project is about the battery cases, motor housing cases. Actually, it's for the cases, and these cases, the now what's used in the industry, 100% from aluminium battery case, but we would like to do lighter these cases, and then the carbon fiber composite is going to play in the role, and it's very famous in the transport industry, especially because of the very heavy and also very high mechanical properties, but very low thermal conductivity. That's why we cannot produce our cases, battery cases, direct the carbon fiber composites. That's why the idea is develop multi-material, then we can have both good mechanical and good thermal performance, and lighter product. Yes. I would like to introduce what kind of material we used in our project. We use different kind of the aluminium, but my experiments in the joining technologies, I have used aluminium silicon titanium magnesium by laser powder bed fusion additive produced. And as you can see, the thermal conductivity of this material, this aluminium alloy, and the melting temperature is very high, especially when we are talking about just the aluminium alloy welding. It's very normal process. But if we would like to produce multi-material joints, for example, short carbon fiber reinforcement PA6 or PEC material, it's very challenging. As you can see, the thermal conductivity of this kind of the composite is lower than 1, and the compare with aluminium is 120, and the melting temperature is very completely different, and it's very challenging to produce them. Here you can see the kind of the example of our products. For example, it's as I said, laser powder bed fusions produce aluminium silicon titanium magnesium, and it's again by additive manufactured short carbon fiber PA6. And when we join them or bond them, we got the multi-material. Sorry. At Fraunhofer IPK, we have an electron beam welding system from ProBeam. I will show lately our machine actually. But beginning of the project, we have to check if we work with this kind of the composite material by electron beam welding technology system. And for example, you can see also here, if you want to weld aluminium material, we need 1 millimeter of thickness aluminium, we need 30 or 40 joule per millimeter energy input. But for this kind of material, although we give very lower than 1 joule per millimeter energy input, the heat concentration direct impact on the point of where is the beam, and at the end the heat is not continued to heat dissipated. Then we see the localized energy input and melting and evaporation. It means we have a limitation. We cannot direct apply electron beam on composite surface. But after this pre-experiments, the idea is becoming it's a novel method. Its name is electron beam bonding, because if we want to say welding, it should be two materials total melt and then join them or bond them. But for when we talk about the multi-material joints, it's not possible, because it's not possible to thermal properties of the short carbon fiber. Then we develop the new idea. We give the energy by aluminum. It means we apply the energy input by electron beam direct on the surface of the aluminum, and then aluminum dissipated this heat to composite part. And for that, we have different parameters. And to produce multi-material, we have developed two different joint types. One of this overlap joint, and another one is the butt joint. The process parameters are similar. We have both beam current, skinning area, and yeah, this is the common process beam. And for overlap, we have overlap joint. We have also overlap area. And for the butt joint, we have also joint thicknesses, because we would like to also produce the protect composite material from the electron beam. And it's also one example how we bond the aluminum and short carbon fiber composites to bond them. We have thermal element always on the aluminum plate, because we have to control and we have to measure the temperature, because we would like to heat aluminum till or by the process temperature of the composite. It means the which degree of the which temperature of the composite material printed. For example, the printed temperature of the short carbon fiber PA is X6 between 270 and 290 Celsius. And the second type of this method is the overlap joint. You can see we have the similar strategy here, and we measure the temperature during the process. Here is the important things. For example, here and butt joint and noble joint, we can bond them in 20 seconds. It's very, very quickly. And we don't need any post-treatment after the joining, for example. But when we compare the other technologies, or it takes just 20 seconds to join them. And now I would like to show how we develop the process parameter and how to affect on the joint quality. And at the end, I will show the optimized electron beam bonding. But we start very basic two material to join them with the 35 millimeter length of the materials, and we applied different current different electron beam power on the aluminum. And the maximum temperature, the aim is the 275 degrees. Then after that, we solve when we apply a lower beam current, and we have the longer heating time. For example, it's here 204 seconds, for example, for when we apply 1 milliampere. But when we apply the higher beam current or higher energy input, and the heating times of course is the lower. But here is important the energy, how many energy per unit area is applied on the surface of the aluminum. That's why we developed new new calculation. It's the uncalculated from the energy per linear, and it means the energy per unit area. And here is the beam current, voltage is the energy, electron beam power. With heating time and disconnect area is the effect of this energy per unit area. And when we see that, for example, you can see also this this graph, how the effect of the electron beam during the heating process. And also when we apply 4 milliampere, at the same time the composite material is burning. That's why we have to not go up like 4 milliampere. We have to work between 2 and 3 milliampere, and the energy per unit area should be also between 20 and 15 joule per quadrat meter millimeter. And yes, and the first results of this experiment, we have to work with 2 and 3 milliampere. Yes, and then after we will apply the tensile strength test, the lab shear test actually, and we saw that the lab shear strength is the almost 6 megapascal and with 5 kilonewton applied. And then the second one was we developed, or was we saw. We used firstly this kind of the manual clamping forces, and we didn't know how to press or how much force we gave the interlayer of the aluminum and the composites material. For example, as you can see here, we applied the same process temperature, beam process parameter, for example, 1 milliampere, and the same maximum temperature, but the lab shear joint strength is quite different. And then after that, we developed new clamping system, because we would like to repeatable process, and we also would like the force should be spread equally. It's the how seems the clamping system. On the top we have aluminum part, metal part, and down we have polymer composite part. We have a clamping plate, it's the window, and we also would like to protect composite from the electron beam, because the first pre-experiments we used without fenster, without windows, without clamping plate, directly on the composite part, and it's also protect the electron beam. Protect the composite material from electron beam. Yes, it's our machine electron beam welding system from ProBeam. It's one of IPK, and it's the new clamping system that we developed and produced. And this time also we also changed the position of the thermal element. This time we measured the temperature directly the contact surface, interlayer surface of between aluminum and composite, and we can direct measure how warm is the aluminum, the contact surface of the composite material. And then we applied 10 different processes. We have stable process parameters. We applied 2 milliampere, and the power is the 240 watt. Overlap strain is 25 millimeter. Scanning area 26 millimeter. 26, and then clamping pressure is the 0.4 megapascal. Here is the only difference is the peak temperature, because we have to stop the temperature reach the process temperature or joining temperature of composite materials, but mostly it's between 280 and 290, this experiment. And as you can see, we have very good promising results. And almost 6 megapascal we reach. We reach the materials. As I said, the joining temperature for this short carbon fiber PA6 is between 280 and 290, and the average lap shear stress is 5.4, and the shear force is also 3,400 Newton. Here is also important for the multi-material joints how to break them, or where is the fracture point, or how to fracture them after the lap shear test. And for example, when we look at the experiment 6 and experiment 19, we see the adhesion between composite and aluminum is very well, and then the multi-material joints is broken on the composite part. And when we look at the experiment 4 and 5, adhesion is also very well, because it's broken also with on the composite, but this time it's not complete broken. This time it's to delaminate from the composite. And the experiment 8 is between these two kinds of the failure mechanisms. And according to literature and according to use cases, and this kind of the fracture failure is acceptable. It's what they want actually, because there are adhesion between aluminum and composite joints. And according to discussion with our polymer parts colleagues, this lap shear strength or lap shear force is the maximum the composite can reach. That's why we have very promising results about these similar materials using with electron beam bonding. And after this optimize and development the kind of the electron beam bonding, we would like to ask, is it possible to use electron beam for complex geometry? It's for normal plate is okay, it's producible and it's repeatable. And what about the complex geometry? We tried also our first demonstrator samples for cylinder samples, for example, and we also joined them successfully very well, and we also shows our very first demonstrator last year at Formnext in Frankfurt. Thank you for joining, and thank you for your attention. Sorry about my voice and my coach during the presentation. Is there any question?
Thank you, IBK. Then thank you, Martha, for the presentations. I think we are ready for questions. So if you have any questions, I think Anna has her hand raised. Okay.
Hi, sorry, it was a mistake, sorry.
No problem. Yeah, if you have any questions, please drop it in the chat box, or you can unmute your mic and
Mega has a question for Martha, I think, in the chat. Is about the friction stability.
Yeah. I'm reading the question. Mega said, thank you for the innovative presentation. I have a question regarding the friction stir welding methods. As mentioned in the presentation, they offer lots of advantages, but are there any specific challenges that we need to pay attention? I can imagine maybe some materials could be unsuitable to be welded with these methods, and also with this process, do they need an extra attention to heat management? Okay, thank you for your question, Mega Christina. Yes, the answer, we need to pay attention on some details. For example, as we said, the relation between the thickness and the dimension of the tool, and I'm talking about the diameter of the solder, also the diameter of the pin and the length of the pin, because it should be close to the thickness of the material to be welded. So this relation, together with the rotation and advance speed, is the critical triangle of parameter in which you will be able or not to process your materials, especially in the similar material. For example, it's important to define if you put, if you are welding, for example, copper and aluminum, if you put one material in the advance side or the retreat side of the welding. As we mentioned, the vectors of the rotation are changing because it's circular, and in some points are parallel and in the same direction, and then they can be the opposite. So it could influence the mixing of the dissimilar materials. So basically, really to clamp the clamping system, to clamp currently the material, and the relation between the dimension of the tools and the thickness would be, for me, the critical points to have a good weldings.
Martha, I think you
And-
have another question from Anand,
Yeah.
I think.
Yeah. My question is for Marta. How metallographic textures improve the weld characteristics? Can we control the texture development during friction stir welding? If yes, how? How much strength improvement you have got to do it to the texture? Okay, this is a very good question. For sure, it is really important for the mechanical, and I'm talking about tensile test characterization specifically. If you have a very high misorientation between the grains, so it means that crystallographically the grades between one orientation and the other is the maximum, so it's really different. It means that the dislocations, advancement during the deformation of this material is going to be more difficult. Okay, so it's not only about the grind size, and as you may know that it follows the hole pitch law. So this hole pitch relation between the grind size as smaller as it is, the highest is the strength, right? But it also has an influence because the dislocations traveling around the material and crossing the limits between the grains is going to be more difficult. So the strength is going to be higher if the crystallographic orientation is very high between the grains. So it means that the texture directly is related with also with the strength of the alloy. So how can I control the texture of the material with friction stir welding? Okay, so the answer is decreasing as maximum as possible the heat input. So if you can process with friction and you can weld your materials using a very low heat input, it means the minimum rotation as possible, or the maximum speed of the tool, it is gonna be translated in a very fine and very misorientated microstructure. So as highest is the deformation and the lowest is the heat input, is better the texture. So I will control the texture this way by decreasing the heat input. Yeah, definitely.
Thank you, Martha. Just before I take any further questions, I would like to remind the participants who have attended the training session today to fill the feedback form that's on the chat box. There's a QR code as well. I think you should be able to scan that. This would really this would be really helpful for us to improve our further upcoming training sessions. So thank you very much. So if you have any more questions, please feel free to unmute your mic, or you can use the chat box as well. I think this question is for IBK.
Yes. The question from Anand. My question is for IBK. How you are able to apply electron beam over so large area, or are you scanning the area using a fine localized beam? Every time we have to write a program, we can produce any kind of the electron beam shape. For example, we can also produce 100 millimeter minus 200, for example. We are so flexible to produce laser electron beam figure shape. It's always flexible. For example, our lab, we have used always square because our lab is also square, but as I showed the butt joints, it was a very longer sample compared with the overlap joints, and it was scanning area 70 millimeter times 10 millimeter, for example. We are very flexible to produce figure shape.
Any more questions? Okay, and if we do not have further questions, I would like to, before we end the session, I would like to just remind our next training session, which is next Monday, which will be on simulating 3D printed metal, CFC, multi-material designs, and joining methods. So this will be conducted by IBK again, and also my colleague Azim. So we would like you to join this training session as well. So if you have not registered already, you can scan this QR code, or else you can also visit the MULTHEM website to get more details about each training session and complete your registration there as well. So if you do not have any further questions, we can end the training session for today, and would like to see all of you again next Monday at the same time. Thank you very much for joining. We really appreciate that. We really appreciate your support, and thank you to our two trainers as well. It was very insightful. Thank you very much, and have a good rest of the day. Thank you.
Thank you. Have a good
you.
day.
Thank you.
Bye bye.
Bye bye.
Bye bye.